go on. Let's find an angle given its trig function. So let's find an acute angle theta such that cotangent of theta is root 3. Now, if we're actually going to find the angle exactly, and I give you a simple expression for the trig function, the only real way we know that is it's going to be some kind of special angle. So root 3, you would expect it's a simple expression involving a square root, and this is the square root of 3 or 2. So it's probably going to be a special angle. Can you go and you find a special angle that gives you cotangent of theta is root 3? Well, we can extend this down to tangent of theta. Right? We divide that by that, so that's going to be 0. That by that is 1 over root 3. That by that is 1. That by that is root 3. There you go. And this by this is infinity. So cotangent is root 3. That's 1 over tangent. So what angle is that going to be? 30 degrees. Good. So we tried one of the two special angles, and we actually find that what works, if you want to just draw the triangle, what works is it's going to be adjacent over opposite. So to get root 3, it's got to be that divided by that. So that's going to be the adjacent of 30 degrees. All right. Another way of it. All right. Sine of theta is 1/3. Do you see 1/3 anywhere up on this table for the sine? No. So this is not going to correspond to a special angle. So how do we find theta in this case? Well, there's no simple exact expression for it, so we'll resort to a decimal approximation. Well, there isn't a simple expression, but it involves a trig function. So no special angles here. So we'll get an approximate angle using say a TI-83. Now, do you calculate, I know they're not TI-83s, but are they TIs? Mostly? Okay. So they're probably somewhat similar to the 83s that have more functionality. So we'll rewrite sine theta is 1/3 using the inverse of the sine function. So recall inverse functions. F of x is equal to y if and only if x is the inverse function of y. If f is a one-to-one function. So now, theta, which we get just by hitting this, using this, or hitting this on both sides by the sine inverse function, theta is equal to the sine inverse of 1/3. So now this -1 here in the exponent doesn't mean reciprocal, it means functional inverse by that terrible abuse of notation. So how do we get this? Well, on a TI-83, you hit the second key, and then the sine, and that turns it into the sine inverse. And you enter 1/3, and this is what you get. Is that in degrees or in radians?
Degree.
That's almost certainly in degrees. In fact, it is in degrees. You would get that if you were in degree mode. If you were in radian mode, you get the angle in radians. So the degree and radian modes also work for the inverse functions as well. Okay? So about 19.47 degrees, or 19.5, rounding to the 3 significant digits. All right, questions? All right. That's in degree mode. So let's do an application. So a 6-foot man is 100 yards away from the base of a tower. He sees the top of the tower and he measures an angle of 55 degrees above the horizontal line. How high is the tower? So here's the man. He's blue. He's 6 feet tall. his eye level is 6 feet off the ground. Is 100 yards away from the tower, and he measures this using a sextant or something to be 55 degrees. How high is the tower? So H. So this is in yards. So let's adopt yards as our unit of length. So this is 100 yards. So if x is also in yards, then in fact the height of the tower is going to be x plus 2 because the guy's 6 feet tall. So that's 2 yards. You add 2 yards to whatever x is. So now find x. X is the opposite of a right triangle whose acute angle is 55. And the adjacent is 100. So we go back to a previous problem, and we say, okay, x divided by 100 is the tangent of 55 degrees. So x is 100 times the tangent of 55 degrees, which is about 143 yards. So the tower is about 145 yards tall. Question? That theta there is there because of the animation. There's a glitch in the animation. We'll see why it's there in a second. So another example. Find the angle of elevation of a 15-foot ramp that rises to a platform 3 feet off the ground. So here's the ramp, here's the platform. The ramp is 15 feet long, and you want to find the angle of elevation. So what do we know? Yeah, we know the hypotenuse and we know the opposite. So the opposite is 3 feet. Feet will be our unit of length. The hypotenuse is 15. So what do we know about theta? Sine of theta is 3 divided by 15. Or 1/5. No special angle corresponds to 1/5 here. So, again, we'll settle for an approximate answer. So theta is the sine inverse of 1/5. Tomorrow we'll talk more about inverse trig functions. We'll do more than it. We'll do them in more depth. So that's coming. So, and if you're in degree mode, you'll get about 11.5 degrees. Which sanity check? Yeah, okay, it's about 11.5. Like that. It's not very big. All right, going on. Now we're going to talk about trig functions of any angle. We've been dealing with acute angles only so far. We are now going to extend trig functions to any angle, positive, negative, any real number. So, here's the idea. When theta was acute, the right triangle was in standard position. If theta was in standard position, you can imagine the origin being right at theta. So, what you could do instead is here's theta. Well, here's the terminal side. So if the adjacent is x and this is y, then, and that's the origin, that's 0, 0. Then what are the coordinates of this point? X1. Okay. Here's what we're going to do now. Now we'll take any angle whatsoever. The terminal side will be somewhere, and we'll pick arbitrarily some point on the terminal line, call it coordinates x and y. So the x coordinate is here, the y coordinate is here. And now notice that x is negative, because it's to the left of the origin. Y is still positive in this particular example because the terminal side is in quadrant 2. So if the hypotenuse is r in the acute case, then we can just write sine of theta is y over r, and cosine of theta is x over r, right? Opposite over hypotenuse, adjacent over hypotenuse. Well, now we just do the exact same thing, but now this terminal side could be anywhere. Okay. So sine of theta is y over r, cosine of theta is x over r, and then we can get the other four just using the trig identities. So tangent of theta is going to be y over x, and it's only defined if x is not 0. Cosecant of theta is the reciprocal of sine theta, so it's r over y. Secant is r over x, and cotangent is x over y. And of course, these might be infinity if the denominators are 0. R is related to x and y by the Pythagorean theorem. R squared is x squared plus y squared. No matter where this point is, R will always be positive. That's the rule. R will always, the ratio, the radius, or the hypotenuse is always a positive quantity. And we're allowed to pick this point anywhere along the terminal side except for the origin. So R has to be positive. It can't be 0. So you can always find R just by taking the positive square root of x squared plus y squared. That will give you R. So in fact, now all of these quantities are just in terms of x and y. You can express R that way. So let's look at some observations. The trig functions of an angle only depend on the locations of the terminal side. It doesn't depend on how you choose x and y. If you slide this point xy along this line, x and y, if you let's say you slide it that way, x and y are both increasing, but so is r. All three are increasing by the same factor, by the same ratio. So these ratios don't change at all. So the trig functions only depend on the terminal side. They don't depend on the choice of where you choose x, where you put x and y. The algebraic sign, in other words, positive or negative, of the trig function depend only on the quadrant where the terminal side is in. So in quadrant 1, all the trig functions are positive. In quadrant 2, for example, the cosine is negative, but the sine is still positive because y is positive and x is negative. The algebraic sign of the trig function only depends on the quadrant. Okay. So let's do this systematically. Which quadrants give you a positive sine of theta?
One and two.
Yeah, it's where y has to be positive, so that's going to be in quadrant 1 and quadrant 2. Because r is always positive. So there we go. And in quadrants 3 and 4, it's going to be negative. That's also true for the reciprocal of sine. The reciprocal of a number always is positive or negative along with the number itself. So cosecant of theta is also going to have the same positive, negative profile of the quadrants. How about cosine of theta? Where is that going to be positive? Yeah, so x is positive, so it's going to be quadrant 1 and quadrant 4. And it's negative in quadrant 2 and 3. All right. Same with secant theta, which is 1 over cosine theta. All right, how about tangent of theta? So notice it's going to be positive just when y and x are either both positive or both negative together. Because if they're both negatives, then the negatives cancel out. So where is it positive there? 1 and 3. And it's negative in 2 and 4. So there's the complete profile of which trig function, the same for cotangent because it's 1 over tangent. That's a complete profile of what trig functions are positive where and negative where in terms of quadrants. All right, so now we're going to do what we did before with acute angles. We're going to try to do this now with arbitrary angles. All right, so let's do an example. suppose the cotangent of theta is 6/5. Now, with an acute angle, that was enough to determine everything else, but now it's not. We need another piece of information. We'll take that the sine is negative. So cotangent of theta is 6/5, and the sine is negative. Find cosine of theta and cosecant of theta. So let's do this. So we could do the following solution. Choose a point xy that gives you the cotangent being 6/5 and the sine being negative. So cotangent of theta is x over y. So we want x over y to be equal to 6/5. So you could take x equals 6 and y equals 5. And that's fine, that would be the first thing, but then the sign is positive. So how can we get the sign negative? Yeah, you can take negative 6 divided by negative 5. That gives you the same ratio. But now y is negative, and so y over r is negative, which is the sine of theta. So natural choice is x equals minus 6, y is minus 5. And if we draw that, we get this point down here. So which quadrant is that? Quadrant 3. Okay. So now the cosine of theta is x over r. So r is the square root of x squared plus y squared. So we have x and y. So we compute this and we get the square root of 61. And we always take the positive square root for the radius. So now we can write down cosine of theta is x over r is minus 6 over root 61. Or if you like, 6 root 61 over 61 minus. Okay. Cosecant of theta is r over y. Plug that in. So it's root 61 over negative 5. All right. We could have used some identities. So, for example, cosecant squared of theta is 1 plus the cotangent squared. Well, we already know what the cotangent squared is. It's 6/5. So the cosecant squared is 1 plus 36 over 25, or 61 over 25. So the cosecant itself is we take the square root of both sides, and we get cosecant is plus or minus root 61 over 25. But now, without more information, I don't know. It could be either of these. But so this is where we need this other piece of information, the fact that the sine is less than 0. So, that's in the way. That should say sine of theta, I'm sure. I'll find it. Yeah, there we go. Okay. Oh, didn't want to do that. Okay. So if sine is negative, the cosecant is also negative. It's reciprocal, so we have to take the negative solution. So you negative 61 over 5. All right. Questions? Okay. There's no simple way of determining theta here. But the point is, we don't really need to know theta. We can bypass theta and just use our identities to get exact expressions for the trig functions. But there is no nice exact expression for theta. So here's the thing that you should not do. Find theta approximately using your calculator, and then using that value, plug that in, and get the other trig functions that way. That will only give you approximate answers. It won't give you exact answers. Okay. Theta actually, there are infinitely many thetas that give you the same terminal line. So in fact, the trig function only depends on the terminal line. And there are infinitely many thetas that are coterminal. So all of these thetas will give you the same answer. Okay. So when evaluating thetas in trig functions, we can always use a specific acute angle. And this will help us to compute some of these things. We can always, if we want, reduce, even if we're not in the first quadrant, we can always put a right triangle in there and go back to using a right triangle as follows. Wherever this line is, take a right triangle with it as the hypotenuse and the x-axis as the adjacent, and the line going from the tip, going from xy to the x-axis, call that the opposite. So the triangle is no longer in standard position, but it's still a right triangle, and it'll tell you a lot about the trig function. So this is an acute angle now. That acute angle is called the reference angle of theta. If this is theta, or that's theta, whichever, this is always an acute angle. It's called the reference angle of theta. So if theta is an angle in standard position, its reference angle is the acute angle formed by the terminal side of theta and the horizontal axis, whichever horizontal axis is closest. Here it's the negative x-axis. If we were in quadrant 4, it would be the positive x-axis. Cosine of the reference angle, in this case, now if you think of all of these quantities being positive, it's 6 over root 61. And the cosine, the true cosine, is going to be the opposite, is going to be the negation of this. Because I'm in quadrant 3, so the cosine is negative. Oops. So this is true in general. So the general rule is as follows. And the trig function of any angle is always plus or minus the trig function of its reference angle. You take the reference angle. The trig function is always plus or minus. The reference angle is acute, so the trig function of the reference angle will always be positive. So you can tell which it is by just determining what quadrant you're in, what quadrant the angle is in. So the sign, whether you take plus or minus, depends on the quadrant of the terminal sign. So let's use reference angles to evaluate, say, tangent of 150. So let's draw 150. There's 150 degrees. 150 degrees. What's the reference angle?
30.
It's 30. It's the shortest angle you can get between it and the horizontal axis. So the reference angle is 30, in this case, 30 degrees. And here is the positivity-negativity profile of the trig function. So is tan 150 going to be positive or negative? It's going to be negative, because I'm in quadrant 2. So it's going to be minus the tangent of the reference angle. So it's minus tangent of 30. So you could just go back to the reference angle and take a minus sign because you know you're in quadrant 2. So what's tangent of 30? It's the special angle. Read it off. It's 1 over root 3. Okay, or minus root 3 over 3. Questions on reference angles? The other thing I like to do is if you can still draw a right triangle and not worry about reference angles. Let's say you're in quadrant 3, for example. Okay. And I guess what was this, root 61, something like this. Since you're going down, that'll be negative. So just put a sign to the legs. The legs could be positive or negative depending on which direction they're going. That's minus 6, and that's minus 61. If I were going up this way, then this would be positive 61, and that would be minus 6. And the hypotenuse is always positive. Okay. So if you do it this way, then the trig function of the angle, you can just read off the ratios like you do for any right triangle, and it'll actually give you the correct sign, the correct. It'll give you a positive number if it's positive. It'll give you a negative number if it's negative. So that's another way of doing it, and it doesn't use reference angles, but you can use either way. All right, how about the cosine of 7 pi over 4? Draw it again. So 7 pi over 4 is just pi over 4 short of 8 pi over 4, which is one complete revolution. So I'm in quadrant 4. The cosine in quadrant 4, is the cosine positive or negative? Positive, right? Red is plus. What's the reference angle? 45 degrees or pi over 4. All right, so these are equal. And this is a special angle. And just read that off, it's root 2 over 2. So that's the answer. Questions on reference angle? Yeah, I can skip this. Okay. Find all angles between 0 and 360 degrees such that whose reference angle is 30. Generally, there are going to be 4 of these, one in each quadrant. So here's the reference angle itself. So this is its own reference angle. Then in quadrant 2, quadrant 3, quadrant 4, they always form an X like this. So they put the terminal sides together. They form 2 straight lines going through. So I'll skip this. I'll skip the rest of this. Well, yeah, because we're going to do something. We're going to do something similar to this later. So I'm going to skip this example. It's often better not to know too many different ways of doing something, because then you just get the tyranny of too many choices and it gets confusing. So I don't think this is really necessary. All right. Well, okay. So this is. I guess this might be more useful than I thought. So we want to find all angles theta from 0 to 360 degrees such that tangent of theta is root 3. Well, that's the reference angle. That root 3 corresponds to 60 degrees. So we're saying, when is tangent of theta equal to tangent of 60 degrees? The reference is 60. Tangent is positive. So you're going to take all the angles whose reference angle is 60, but only take the ones where tangent is positive. So that's going to be quadrant 1 and quadrant 3. So you take that angle and that angle. That's actually a straight line. It doesn't quite show up very well, but that's a straight line. So it's 60 and 240. Those are the 2 solutions. Notice this is true in general. If you take a line and you add 1/2 revolution to it, so 2 angles that differ by half revolution have the same tangent, because you are flipping the sign both of the numerator and the denominator. So you get the same tangent. So in general, we have there's another identity. The tangent of theta plus 180 degrees is equal to the tangent of theta. This is true for any theta. Also, you can write it as a tangent of theta plus pi is equal to the tangent of theta. I'm going to go back a slide and see if there was something that I should talk about previously. Nah. I'll write about that. Okay. The tangent of an angle. If you take the line, the terminal side of that angle, and extend it in both directions by adding a half revolution, the tangent of the angle is the slope. Is the same as the slope of the line. So here the line has positive slope, and the tangent of either angle, either this one or that one, is the same. It's positive. If the line goes like that, it'll have negative slope, and the tangent will be negative. So the tangent is actually equal to the slope of the terminal side. Always. Rise over run. Y over x. Rise over run. Okay. All right. Okay. Going through all this pretty quick. Similarly, the sine of pi plus 180 is minus the sine of theta. This is because they have the same reference angle, right? But now, in opposite quadrants, the sine and cosine flip from positive to negative and back again. So if you're in one quadrant and you look at the sine and cosine and they have a particular algebraic sign, you go to the opposite quadrant, both of those algebraic signs flip. So the sine of theta plus 180 degrees is minus the sine of theta, and likewise the cosine of theta plus 180 degrees is minus the cosine of theta. Okay. Let's do an example. So given that the cosine of theta is 3/5, find the cosine of theta plus pi. Just tell me what it is. It's negative 3/5. Yeah. Okay. Animation is screwy. Don't know why. Cosine of minus theta. Tell me what that is.
Cosine of theta plus pi.
So here's theta. Let's say it's acute. Minus theta is like that. Same reference angle, but if theta is in quadrant 1, minus theta is in quadrant 4, cosines have the same algebraic sign. And that's true, say, if I'm in quadrant 3, then minus theta, in quadrant 2, then minus theta is in quadrant 3. Same algebraic sign for the cosine, same reference angle. So this is in fact equal to cosine of theta. Sorry, this animation is screwy. I'll just put out the whole slide and talk about it. All right. So theta and minus theta have the same reference angles, no matter where they are. So their cosines have the same algebraic sign. So the cosines have to be equal. Okay. What about sine of minus theta?
Negative.
Yeah, it's negative sine of theta, because now they have the same reference angle, but now the algebraic sign of the sine function flips as you cross the x-axis. Because the y-coordinate, the sign of y goes from positive to negative and vice versa. So sine of negative theta is actually negative sine of theta. All right. So we get some more identities. Cosine of negative theta is cosine of theta. Any function that satisfies this, where f of minus x is equal to f of x. That's called an even function. Its graph looks the same on one side. This looks the same reflected in the y-axis. Looks the same on one side as the other. Any function f of x that satisfies f of minus x is minus f of x is called an odd function. This says that sine and tangent are odd functions. If you look at the graph of an odd function, it looks the same if you rotate it 180 degrees around the origin. Okay. So an even function might look like this, and an odd function might look like this. Okay. Rotate that 180 degrees, looks the same. Flip that in the y-axis, looks the same, so it's even. So let's do one more of these. Given that sine of t is minus 2/3, find the sine of minus t. Just 2/3. Because it's negative sine of t. And so it's negative 2/3, which is plus 2/3. Okay. Sine of pi minus t. Oh, gosh. Can you do this? Let's see what the slide says. The slide says it's sine of minus t plus pi, certainly, okay. So, recall that the sine of theta plus 180 degrees, so that's the same as pi, is equal to minus sine of theta. So this, because that's the plus 180 degrees there, this is going to be minus the sine of negative t. And now, I can use sine of negative theta is minus sine of theta, and plug that in here, so that I get minus a negative sine of t, which gives me just sine of t, which is just 2/3. Okay. Or I guess I'm using part A for that. All right. Sine of t plus 2 pi. Yeah, this is just sine of t, right? Because the trig function only depends on the terminal side, and t plus 2 pi is one complete revolution, so t plus 2 pi and t are coterminal. It's the same angle, so all the trig functions are equal. So not just sine, but cosine, everything. They're all equal. So sine of t plus 2 pi is just the sine of t, which is, again, minus 2/3. And this is true for all 6 trig functions. So in general, any trig function, if you add a complete revolution to the angle, you get the same value of the trig function. So trig functions of coterminal angles are equal. Any function that satisfies something like this is called periodic. And the length of the period is what's the length before it starts repeating. And in this case, the length is 2 pi. For sine and cosine, it's 2 pi. The tangent function actually repeats after pi. So the tangent of x plus pi is equal to tangent of x. So that actually has a period of half a revolution. Okay. Almost break time. So, for example, cotangent of 390, 390 degrees, subtract off one revolution, which is 360 degrees. So this is the cotangent, cosine of 30. That's what's left. And read that off as √3/2. Special angle. Questions on this? I don't know what we're doing. All right. So finally, just briefly, talk about the unit circle. So remember, we said that you could pick x and y anywhere along that, and then take ratios. So let's pick a particularly nice choice of x and y. Let's make the radius equal to 1. That simplifies things a lot. So if we make the radius equal to 1, then sine is just the y-coordinate and the cosine is just the x-coordinate. Really easy. So the x, you could just read off the cosine and sine just by looking at the x and y coordinates. So the points, the possible points where the radius is 1, form a circle around the origin with radius 1. This is called the unit circle. So now we come to it. In the unit circle, x squared plus y squared is equal to 1. And the point xy is cosine theta sine theta, where theta is the angle that you get to hit that terminal side. So it's nice to work with the unit circle, because things simplify a bit. So let's find the points on the unit circle corresponding to some special angles. Well, first of all, angle 0. Where is x and y?
They're along their axes.
Yeah, it's right there, right? So x is equal to 1, and y is equal to 0. So that's 0.10. So that immediately tells you what the cosine of 0 and the sine of 0 are. Cosine of 0 is 1. Sine of 0 is 0. Okay. T is pi over 6. That's there, and that's a special angle. So this is 30 degrees. And so x and y are the cosine of pi over 6 and the sine of pi over 6. That's root 3 over 2, 1/2. So just reading off of there. So that's that point. Then the next special angle is pi over 4, which is 45. It's that point right there. And so that point is root 2 over 2 and root 2 over 2. So about 0.71 for both coordinates. So this is actually on the line x is equal to y. So those are the same. And finally, pi over 3, 60 degrees. It's right there. Well, this is actually just a reflection of this through that line, so you can just swap the coordinates around. And it's 1/2 root 3 over 2. That's it. And finally, for t equals pi over 2, this is 90. What's x? X is 0 and y is 1. Okay. So cosine of pi over 2 is 0, sine of pi over 2 is 1. All right, unit circle. We can keep going around the unit circle. So if we go into quadrant 2 and we take t is 2 pi over 3, that's 2/3 of the way. Well, notice this is just a reflection of pi over 3. So it has the same y-coordinate and the x-coordinate flips. So I'm going to get a minus 1/2 and the same y-coordinate, 3/2. And I'll skip this. Is that me doing that? No. Let's look at the graphs. Well, let's not. Let's take 10, and then look at the graphs.
Yeah, it was me. I was looking through the graphs, and it
Ding ding.
Yeah, it hung up on the slide.
Yeah. Is there a way you can?
Times and then went to the last slide. I was like, we can't go any further with the ding ding.
Right.
Because I thought it was me. The sound coincided with you doing that.
Is there a way you can turn the sound off?
Mute your computer.
Yeah, there we go. Off now.
Okay.
Sorry.
No, it's all right. It's all right. It's just a minor distraction. Yep.
Clean break.
Simply like. Salute. I usually a lot during
Does anybody else have toys for the toy drive? I might go over there for lunch anyways. Toys for the toy drive for ops. We got two in my trunk. I'm really proud about. I'll throw them in there and be after the deadline. But now they just swim around with I mean, you can admit it's there. It's actually but it's with cartoons, right?
Up in the back, really. So the
What?
Is it the blacked out windows?
You don't look at no window.
It's pretty good. It sells his ice cream too.
Well, that's only if you have skills tattooed on hand that they don't have a real tattoo.
Horrible. Yeah.
That's what it is.
So funny.
That was a joke I actually got off. But that's so lame. I've been eating freaking cough drops like candy, which will essentially do something.
It should be
balls nasty.
You never really got to get here for this meal, like all the place.
I used to always go to menu, numbers, or
Just go off about 45 on this shit, so. I'd have been running up like this. Come on, me. There's a bright stuff. You guys don't have it, where they show like the Egyptian gymnastics thing, like the Egyptian parasleepers. And I don't know if they just grabbed the guys like off the street that day or what the deal was. Because you have them like falling down on the like going out the door and the gymnastics kicking them out. So. Well, I'm sitting having on my iPad.
If you don't exit the aircraft, you're going to get fried.
You don't have a positive exit, you're going to hit the aircraft. Or do you think within your own equipment? That's what I find.
I saw that when I was coming.
I saw that. I appreciate to see someone else still needs to get like a first year.
You know, the thing about it is, they change too much. It's iterative in cycling and new combined. It's the same.
I don't have it, but I do have the whatever.
All right. Final push.
Let's do it.
Let's do it. Last hour. So in the final hour, what we're going to do is we're going to look at the plots of some of these trig functions, and we will solve some simple trig equations, and we'll call it a day. So let's do the sine and cosine functions first. So, excuse me. Here we're going to graph the function y is sine of x, and we'll do it if in the interval 0 to 2 pi. Because we know outside this interval, the function repeats itself, so it looks exactly the same. So we know sine of 0 is 0, and now just some highlights. Well, we got the special angles here, so sine of pi over 6 is a half, root 2 over 2, root 3 over 2, 1, and then it goes back down. It comes back down and it hits negative 1. So right at pi, it's 0 again. And it's 3 pi over 2, it's negative 1, and then it comes back up to 0. So here's what's going on. So take this point, start it at the point 1, 0, and you're just rotating it around the unit circle. Okay? Look at the y-coordinate. How is the y-coordinate changing? It's going up, it's going back down to 0, it's going down to negative 1, and then coming back up to 0. So just the horizontal, the vertical displacement is the sine function. So a couple things to notice. There's lots of symmetries here. So if you, for example, if you rotate the graph around this point 180 degrees, just like that, it maps to itself, looks the same. That's the same at any 0 point. Because this function is periodic, if you go into negative territory, it just looks the same like that. Or positive, it looks the same like that. It just goes like that forever. So if you rotate it around 180 degrees around any of the 0 points, rotate the graph, it'll look the same. If you reflect the graph in one where it reaches its apex, or where it reaches its anti-apex, I don't know if there's a word for that. Nadir, trough, whatever. Okay. If you reflect it in that line, it'll also be symmetrical. Okay. So this piece looks a lot the same as that piece. And likewise, that piece looks the same as that piece. So you can use these symmetries to actually, if you find one solution to an equation, you can use these symmetries to find other solutions as well. We can do that using the graph. That's what the slides do. I'll give an alternate method on the board when we get to it.